So welcome to the One World Probability Seminar. Today we are very happy and very excited to see the talks of Milton Jara and Octavio Menezes. We will start with Milton Jara, who is a professor at IMPA in Rio de Janeiro, Brazil, and he will talk about non-equilibrium stationary states. Thank you for being here, Milton.
Thank you very much for the invitation. So my talk is going to be sort of introductory, so it's not going to be very heavy on technicalities. And what I want to do is to explain you at least what we understand as a non-equilibrium stationary state. Why do we think it is interesting to study this non-equilibrium stationary state, and what is our propositions, our framework to work in this problem. Okay, so we start with a little bit of real examples. Okay, so basically the idea is that somehow I have to do something here, maybe. Okay, yeah. So the idea is that non-equilibrium stationary states are found everywhere. Okay, so in nature, in physics, and you always find these non-equilibrium stationary states. And then this is one example which I found particularly interesting, which is a hurricane. Okay, so in a sense, a hurricane is in a stationary state because it doesn't change too much with time. And so it keeps basically being the same for some time, and then of course it's not what we think about at first sight of what stationary means. Okay, because there is a difference in physics between what people call equilibrium and what people call stationary state. Okay, so a stationary state is a state which is it doesn't change with time, but an equilibrium state is a state which on which there are no currents, and of course in a hurricane there are lots of currents. Okay, and so this is kind of an example of what a non-equilibrium stationary state is, and there are many others. Okay, so so this is another example. So it's the flow on a river. It could be thought of as an equilibrium stationary state because again, the flow is stationary in time, but of course there are currents which can be very complicated. Like for example, this example of a waterfall. Okay, so these non-equilibrium stationary states are everywhere. So this is another one that's also non-equilibrium stationary state. This is the sun. Okay, so one of the striking reasons why life is possible on Earth is because the stars are very stable in time. Okay, so the amount of radiation that Earth receives from the sun is strikingly stable in time. So you can think about the sun as a stationary state, but again, it's a non-equilibrium stationary state. There are lots of in the case of the sun, there are radiative currents, convective currents, etc., that drive the process inside of the star. Okay, so all of these are examples on the non-equilibrium stationary states, and I try to select a sort of dramatic examples because what I want to say is that non-equilibrium stationary states are very complex. Okay, so if one wants to have a sort of mathematical mathematically sound description of non-equilibrium stationary states, it's going to be a very challenging problem. Much more challenging than describing equilibrium states. So in thermodynamics, for example, equilibrium states are usually described by you have very few parameters, and that's it. I mean, it's just like in an ideal gas, there is a volume, pressure, and temperature, and that's it. But when you start to have these currents, you start to get into trouble in order to describe these states in a mathematically sound form. Okay, so well, there are some attempts, of course. I mean, people talk about vorticity, for example, and things like that, but there is not like a unifying framework to work with. Okay, so this is something that could be an equilibrium stationary state. Okay, so this is Salar de Uyuni in Bolivia, so it's a very stable thing. So, but it's of course it's wonderful and beautiful and marvelous, but it's a little bit boring as an example compared with the previous ones, right? So the try to describe the sun or hurricane looks more exciting than try to describe the Salar de Uyuni in a sense. And so now let me tell you what we understand as non-equilibrium stationary states. Okay, so one way to do this is to think about what are the key features. Okay, so as I was telling you before, I mean, as a general concept, an equilibrium stationary state is a stationary state on which currents prevent the system to be in equilibrium. Okay, what type of currents? Okay, there are thousands of possible types of currents. Okay, so it's really a very extensive list of possible currents that can drive systems out of equilibrium: magnetic currents, electrical currents, thermal currents, like when you have a convection, radiative currents, fluid currents, which are probably the most noticeable. I mean, the ones that we can experiment in real life in a simpler way. But even when you have fluid currents, there are differences. I mean, between liquids and gas. So it's there are lots of things that can happen. So there is a way on which one can understand this non-equilibrium stationary state, which is kind of in a sense a negative way. Okay, so equilibrium stationary states, okay, at least from a thermodynamic point of view, are very close to what we call reversible invariant measures in the realm of Markov processes. Okay, so okay, we are probabilists, so this is the one-word probability seminar. Okay, so we don't have any trouble about thinking about the world as an stochastic process. Okay, so the world is a huge stochastic process, and therefore we're happy with the modeling different phenomena with the stochastic process, in particular with Markov processes, because somehow the Markov property is what we understand as causality somehow in the real world. The arrow of time is basically what leads to the introduction of the Markov property in Markov processes. So then equilibrium systems comes to our mind as reversible measures. So reversible, inversible measures, there is no arrow of time. So if you run a Markov process in equilibrium forwards or backwards in time, you get exactly the same law. So this is what we call a reversible process in the context of Markov process. It's not that if we run it backwards and forward in time, we get exactly the same trajectories, but that we get the same laws. And of course, currents prevent you to do that, because if you reverse time in a process with currents, what you will observe are the currents in the reverse direction. Okay, so it's a symmetry breaking fact, the fact that we have currents in the system. Okay, so that means that the equilibrium stationary states at what we call reversible invariant measures of Markov processes. Okay, since to begin with, I don't want to be super technical. Instead of considering Markov processes, I'm going to consider Markov chains, just because for Markov chains we don't have troubles making sense of whatever formula we want to write down. Okay, so from a probabilistic point of view, a non-equilibrium stationary state is going to be an invariant measure of a non-reversible Markov chain. Okay, so there is a theorem which is not that famous, but it's very simple. And so in particular, I always put it as a question on my exams in Markov chains when I teach Markov chains, is that a Markov chain is non-reversible if and only if there is a cycle on which the probability of going in one direction of the cycle is different from the probability of going in the other direction of the cycle. Okay, so that's an if and only if condition for being non-reversible, which is basically the negation of the detailed balance condition. Okay, so a Markov chain is reversible if it satisfies the detailed balance. So what does mean not satisfying detailed balance? It means that you can find this cycle where this is happening. So here there is a catch, which is that this condition does not make any mention about the invariant measure. So it's you can detect whether a Markov chain is non-reversible without knowing what the invariant measure is. Okay, and this is interesting for our point of view, because we want to somehow put on a mathematical framework these ideas of non-equilibrium stationary states, and we have already seen that non-equilibrium stationary states are very complex. So they have complex structure, complex dynamics, and if in particular there is some sort of unpredictability of them, so you never know when a hurricane is going to appear or things like that, and from that point of view, it's nice that you can tell whether a Markov chain is non-reversible without actually looking at its invariant measure. Okay, so so now my initial goal was to study this non-equilibrium stationary state that appears in real life, let's say, and now I'm translating this question into a mathematically sound question, which is the study of the invariant measures of non-reversible Markov chains. Okay. Of course, up to here we haven't really advanced anything in terms of the problem itself, but at least now we can state a mathematically meaningful question that, at least in some sense, is related to the more applied or the more realistic question of non-equilibrium stationary states in physical or biological systems. Okay, so as I was saying, this theorem about cycles tells you that we can identify whether a system is non-reversible without really knowing its invariant measure, which is it's very nice thing. And so the consequence of that theorem is that non-equilibrium stationary states are not necessarily explicitly known. But that doesn't mean that they are not really explicitly known. It might very well happen that for most interesting systems, you can actually find the non-equilibrium stationary states. But general fact is that that's not the case. Okay, so in general, you define your very reasonable probabilistic model, which is non-reversible, and then you cannot really find explicitly what is the invariant measure of this non-reversible Markov chain. Okay, that's what I meant by non-equilibrium stationary state are usually not explicit. Okay, so let me give you an example. Okay, so this is it's a very popular example because it's incredibly simple to define a Markov chain, and it's the structure is so rich that you can do enormous amount of work on top of it. Okay, so the example is the exclusion process. Okay, so the exclusion process is in a given graph, finite graph, is a continuous time Markov chain. Okay, so what you do is that basically you have particles, a certain number of particles on your favorite graph, and they move on the graph following the exclusion rule, meaning that at each time, at most one particle per side. Okay, so two particles cannot share the same spot. So how the dynamics work? So each particle has some internal clock, which sounds right. So in what I wrote here, so the internal clock has rate 2 because you have two neighbors at each place, and then when the internal clock rings, the particle try to jump to one of the neighbors. The symmetric part of the symmetric exclusion process means that you choose your neighbors in a uniform way. And then if there is a particle at the other side of the edge of your graph that you're trying to cross, you don't perform the jump. So you only perform the jump if the arrival site is empty. And this happens independently for each particle. They have this interaction because whenever you find that your arrival site is already occupied, you don't perform the jump. So it's in a sense it's a censored version of just independent random walkers. Okay, so there is a rejection rule for each one of the jumps of the independent system, which is that at most one particle per site, and that's it. Okay, so well, it's a conservative particle system because the number of particles is constant in time, and then but you can describe more or less explicitly what are the invariant measures of this system. Okay, so the invariant measures is basically so it's so products of Bernoullis are invariant where the weights are proportional to the invariant measure of just one particle in the system. There is some computation to be done, but and there is a conservation law, so you have to condition these product measures to the initial number of particles to get an ergodic invariant measure. So that are very easy to describe, and now something that you can do to get, and it's going to be reversible, okay? Because basically you have the tail balance, and that's just the consequence of the fact that the simple random walk the simple symmetric random walk on a given graph is reversible. So one way to take it out of equilibrium to take the system out of equilibrium is to introduce reservoirs. There's one possibility. There are other possibilities. Okay, I'm just taking reservoirs because it's the simplest one to visualize. So here in my picture here, what I'm doing is that I'm putting reservoirs at the boundaries of an interval. Okay, what does it mean reservoirs? It means that when a boundary site is empty, one particle can arrive with some rate, which in these cases are alpha and beta. And when the site is occupied by the particle can get out of the system with the complementary rate of 1 minus alpha, 1 minus beta. So when alpha is different from beta, in this case of the line, you have a tendency of particles to go from the highest density reservoir to the lowest density reservoir. So effectively, if alpha is smaller than beta, you will have a flow of particles from one side of the interval to the other side of the interval. So it generates a current of particles, and therefore it's a non-equilibrium stationary state. This change is irreducible, so it has a unique invariant measure, and it could be very complicated to describe. Okay, so in the one-dimensional nearest neighbor case, okay, so the one that I drew here, you can actually compute the non-equilibrium stationary state using what is called the Derrida's matrix ansatz. Okay, so which is it's a version of the Bethe ansatz. So in particular, it's explicit, but it's not that you can just write down formulas very easy. No, it's a complicated explicit formula. But in general, so if you do anything, you change anything in this model, I mean, instead of having an interval, you have, I don't know, a square, or instead of having two reservoirs, you put also a reservoir in the middle of the interval. If you do any perturbation of this system, you get, in the general case, you don't get this explicit formulation of non-equilibrium, what a non-equilibrium stationary state should be. Okay, so that just to say that it's a difficult question to analyze this non-equilibrium stationary state. Okay, so now what we want to do is inspired by Monte Carlo somehow for MCMC, Monte Carlo, Markov chain Monte Carlo. In Markov chain Monte Carlo, you want to simulate a measure, a given measure. And the way to simulate this measure is to set up a Markov chain that has this given measure as an invariant measure. And then the question of simulating the Markov, the measure is translated into the question of simulating the Markov chain. And in many situations, it's much easier to simulate the Markov chain than to simulate directly the measure that you want to simulate. So this has been amazingly effective in so many places, and there is a huge literature about it, so I'm not going to enter into the details. But what I just wanted to mention it because that inspires us to study non-equilibrium stationary states through Markov chains. Okay, so how does it proceed? Okay, so the non-equilibrium stationary state is the invariant measure of the Markov chain. So let's study the Markov chain. And let's try to send t to infinity. That's it. Okay, so if we can do that, then we get information about the non-equilibrium stationary state. Okay, so from a simulation point of view, well, you just don't need to describe it in mathematically. You don't want to really prove theorems, but you just simulate and see what happens when you take a longer simulation times. But if you are into the mathematical way of thinking, then you have to prove something about it, you know? And that means that you want to send it to infinity somehow. And that points out to another thing, that it's we want somehow before that. Okay, so we want somehow to design methods which are quantitative for to an analysis of Markov chains. So methodology that's it's a little bit opposite to what we are used to do, no, in Markov chains or in limit theorems in probability theory in general, no, that we use sometimes ergodic arguments, convergent distribution, things like that, and that's a type of setup is not so well suited for quantitative estimates. Okay, so let me just here I'm just giving a setup a little bit of definition so we know what we're talking about. So I prefer to always prefer to work in continuous time because somehow it's more natural when you do simulation, when you do Markov modeling. I mean, when at least in statistical mechanics context, continuous time is more natural. Okay, so I'm going to take a finite state space. I'm going to take a Markov chain there, continuous time. So I want to talk about the generator, which is written there. So it's just that to fix notation. So I'm going to consider reducible Markov chains. It's not fundamental that because you can always take the reducible components if you need to, and we want to develop these quantitative methods to analyze Markov chains. And so the rules of the games are the following. So we cannot use reversibility because we want to study non-equilibrium stationary state, which are not reversible. We cannot make use of the knowledge of the invariant measure because in general we don't know it. Okay, maybe existence is okay. Okay, so maybe you can use some information about the invariant measure that you know a priori. Like for example, maybe in a continuous space setting, you know that the invariant measure has a density with respect to the Lebesgue measure, things like that. That could be okay, but not explicitly knowledge of the invariant measure. And we want to make it quantitative because if we make it quantitative, maybe we can take t to infinity, no? Because we will have something like t divided by n, and then we can take t large. So the first set, okay, so a quick definition. So some object that pops up in our methodology, which is not so popular maybe in the concept of Markov chains, is what is called the Carré de Champ, which is this is a bilinear operator associated to the generator, which is very, in case of Markov chain, has a very simple expression. You just take, instead of taking the difference of the functions when you make a jump, you take the square of the difference, and you can generalize it to what I call the L variation. Instead of taking the square, you can take any integer power L. Okay, and that gives you a multilinear operator gamma L. So inspired by statistical mechanics, we want to use relative entropy. Okay, so that's a nice object for many reasons, and it's in principle it's a way to measure the distance between probability measures. Okay, it's not really a measure, but by Pinsky inequality you can estimate the total variation distance in terms of entropy. So although it's not exactly a measure, the relative entropy, it can be used as a way to compare the closeness of two probability measures. Okay, so something which is really nice about relative entropy is that it satisfies duality. So variational principles are always nice because allows you to do a little bit of analysis on top of what you are doing. And there is a formula for the relative entropy. So this is sometimes called Donsker-Varadhan variational formula because it's slightly different from the formula that you can derive from Legendre transform, but it's somehow the same. And from this variational formula, you get an inequality. So you can estimate integrals instead of relative entropy. So you can change the reference measure from nu to mu, paying the cost of relative entropy in this way. So relative entropy is nice because we have something that we call Gauss inequality. So I just wrote down this slide, so you have all the definitions you need to make sense of the following proposition. And I don't want to explain it in detail, so I just wanted to show you Gauss inequality. Okay, so Gauss inequality tells you that the relative end. So you fix a moving frame of reference measures. So the idea is that you have a Markov chain which can be complicated, but some reason you suspect that this Markov chain is closer to a simpler Markov chain, for which you can compute the distribution. Okay, and you use that distribution as a reference measure, and it's moving in time because the simpler Markov chain evolves in time. Or maybe it's not a Markov chain. Maybe you get to this answer from another point, from another side, and then you want to compare the relative entropy of the law of your Markov chain with this reference measure mu t. And it turns out that the Gauss inequality is a very satisfying inequality because it tells you that the derivative of the relative entropy is bounded by two terms. Okay, one which is negative, which looks like an energy in a sense because it involves this Carré de Champ. So remember that this Carré de Champ was a quadratic positive definite form. So it comes here with a negative term, so you can think about it a little bit like an energy, at least in terms of functional inequalities. And there is a second term, which is entropy production term. So entropy is decreasing in a Markov chain, but only if you use the right reference measures. Okay, so if you use the invariant measure as a reference measure, the entropy is decreasing. But we don't know what the invariant measure is, so we get you make a hint, and then there has to be an entropy production term because you have this this fact that the entropy cannot be exactly decreasing, and the entropy production term can be computed explicitly in terms of the generator of the process and the reference measure we're using. Okay, so this is called Gauss inequality, and it's very nice because in particular it doesn't make any assumption. I mean, it works. It's always true. Doesn't rely on reversibility or the knowledge of the invariant measure. Doesn't rely on it. Of course, when you have a super general inequality, it cannot be always useful because it's too general. And so how to make Gauss inequality into a useful inequality is the main game. Okay, so and that comes from the choice of the reference measures. Okay, so sometimes, especially when you are doing sort of renormalization arguments, you have candidates for this reference measure. So usually what you do is that you take one answer, one first order or zeroth order approximation for what you think the law of your Markov chain should be, and you use Gauss inequality to measure the quality of this guessing. And after that you get second order informations about your Markov chain, and you can actually refine your guessing. Okay, and that's pretty much in the spirit of renormalization. And if you can join this Gauss inequality with functional inequalities because of all these variational formulas that you have at your disposal, then it gets very powerful. Okay, so in particular, if, for example, you have access to sub-log Sobolev inequalities or something of the sort, you start to get very, very good information about your Markov chains out of that. Of course, log Sobolev inequalities is a very useful tool in continuous space setting because of Bakri-Emery, for example, or other type of arguments. But in discrete setting for finite state Markov chains is more difficult because log Sobolev's inequalities are not so easy to prove in discrete setting. Okay, so discrete setting is too sensitive to rare events, and then you lose the log Sobolev inequality. Okay. So I wanted to use this maybe it's, and then the minutes I have left to explain you, to give you another type of methodology that it's also quantitative and not really, and it doesn't rely on reversibility or things like that, which is Stein method. Okay, so Stein method is a very clever way to prove quantitative CLTs. Okay, so to really go into the central limit theorem and get a speed of convergence. Okay, so there is an enormous amount of literature about Stein methods, and so just to give you an entry point to the literature, I really recommend these notes by Ley, Reinhardt, and Swan, which are published in probability surveys. But there's a huge amount of things around. Okay. Surprisingly, for Markov chains, there's not that much in the literature, because usually what happens is that in a way, it's like this discussion I gave you before about Monte Carlo. So in Markov chain Monte Carlo, you have a measure and you want to obtain information out of this measure. Then you construct a Markov chain which has this target measure as the invariant measure, and then you run the Markov chain to get information about this measure. Okay, but in that part, in the Markov chain Monte Carlo, there is something which you have the freedom to choose the Markov chain. So usually you can choose the Markov chain in a clever way to make things work better. But in Stein method, it's a little bit of the same. There is something called the semi-group approach, on which you have the measure for which you want to prove CLT, and then you try to construct a Markov process or a Markov chain which has this target measure as the distribution of time t, or as invariant measure. Okay, so this is how Markov chains enter into the Stein method. But if the Markov chain is given to you in advance and you cannot change it because it comes from modeling some physical, some biological phenomenon, it's more difficult to make this Stein method work. I mean, at least the literature is not really, it's not the way people think about Stein method in the literature. Okay, so how do you apply Stein method to Markov chain? So this is, so we start with Dikkin's formula. So the idea is that one way which has been is very powerful and very fruitful to analyze Markov chains or Markov processes in general is through martingale problems. Okay, so you want to show that some object has a limit, for example, a Gaussian limit, and what you do is that you write the object that you want to show that converges to Brownian motion or something like that as a martingale plus a rest. And then you show that the martingale converges to what you want to prove convergence, and you prove that the error term is small. Okay, so that's basically a very hand-waving way of describing the martingale method. Okay, and you have this linking formula that relates the functions of your Markov chain with martingales. Okay. So now you want to show, so what I want to show you is a way to show a quantitative CLT for linking martingales. So the question is that whether this martingale is close to Gaussian, and the first intuition we have about it is that if the quadratic variation is close to constant, then the martingale should be close to Gaussian, because then it will be like a Wiener integral with respect to Brownian motion. You can start to think about representation theorems for martingales. This first intuition is wrong because of Poisson process. Poisson process has a constant quadratic variation, and so not Gaussian. But this Poisson process, which is a counterexample, is also hints into what is missing. because the Poisson process, if you take t very large, then it looks like a Gaussian random variable because of the CLT for Poisson random variables. And so what does it mean to take a large t in a Poisson process if you bring this t back to fixed t? It means that the jumps are small. Okay, so if a martingale has these two properties, the quadratic variation is close to constant and the jumps are small, then it should be the final value of this martingale should be close to a Gaussian random variable. Okay, so how do we implement this this in practice? So we have a theorem. So this is our well, if you do a talk in mathematics, at some point you have to at least to state a theorem. Okay, this is the theorem I want to state now. So let me give you some function phi. So the function phi is, in a sense, so it's the instantaneous quadratic variation. At least is that what should approximate the instantaneous quadratic variation of the martingale. So then we define the variance. Okay, so this sigma 2 is basically the accumulated variance of what it should be the limit of the martingale. We define and we define 5 constants. Okay, so gamma 2 is the distance between the quadratic variation and the constant we are compared with, and this is has to be weighted by the variance. Okay, that has the right scaling. So it's at least in that way you can convince yourself that this is the right object to look at. Then we need to measure the size of the jump somehow. And the way on which we are going to measure the size of jumps is with these L variations. Remember that these L variations look at the jumps of the are powers of the jumps of the Markov chain. So if the third variation, the fourth variation are small, it's probably because the jumps are small, or maybe because the large jumps have very small probability to happen. Okay, so that's a way to measure this smallness of jumps. So we define this gamma 3. Notice that the gamma 3, you have to define gamma 3(1) and gamma 3(2) because the integral defining gamma 3(1) is usually not convergent, because if phi is more or less constant, then sigma grows linearly, sigma square grows linearly in time. So you integrated something divided by 1/t, which has a logarithmic divergence. So that's why you have to take out a portion of the integral. And the same thing, you define the same thing for the fourth variation. Okay, so and you have a similar formula. And these exponents that appear there are making these numbers have the right scaling. And then we have a theorem. And the theorem is that the Wasserstein 1 distance, okay, so the Kantorovich distance between the law of the martingale at the final time ft and a Gaussian random variable of the what you think is the right variance is smaller than this number there. Okay, so it's a number. So and you see that this is and this is typical of this Stein type of methods, no? So you really get a bound, and the constant C is just a constant that only depends on doesn't depend on anything. It's a universal constant. You can even compute it. It's related to the Gaussian law, mid polynomials, things like that. And so you get a completely quantitative estimate between the distance of your martingale and a Markov chain. And then when you have this completely quantitative estimate, of course, there is a question whether this estimate is good or not for your purposes. Well, it could be good, it could be bad, but the good news is that it's explicit. So it's quantitative. So in particular, you can see if you can send it to infinity. So if your estimate is good enough, then you can send it to infinity. Then you start to get information about the invariant measure of the Markov chain. And so therefore, these are the two methodologies that I wanted to present as this relative entropy and this Markov chain-Stein method that allows you to have quantitative information about Markov chains. And if this quantitative information is good enough, also quantitative information about the invariant measure of these Markov chains, which is the information about these non-equilibrium stationary states that we wanted to obtain. Well, I think I'll stop here. Thank you very much for your attention.
Thank you very much for a very nice talk. Do we have questions? I have a question about the part where you were talking about the SEP, and you were saying that the stationary distribution is known, but it's extremely complicated. So what exactly does that mean? It's like it's written in some integral way, or
so let me go back to the slide is not going to help you really, but and so it's based on beta ansatz. Okay. So the matrix ansatz of the readers is somehow a simplification of beta ansatz that works for this particular situation. Works very well for this particular situation. But the formulas that you get from this matrix ansatz gives you correlations. So if you want to get 1-point correlation, it's just the 1-point correlation. You can do it. I mean, it's easy. Then you go to the 2-point correlation. Then you get some formula that integral formula maybe that is you can. It's not so difficult to evaluate in this case. Then you go to 3-point correlation. There's some sort of induction that you can do. And then you start to get more and more integrals on your expansion, and it gets more and more complex. But and then okay, it's up to you whether it's up to your abilities on evaluating integral contour integrals and things like that, whether this is super complex or not. But in principle, you can extract all information you want from this formula. Okay. But this is only for this particular case. I mean, if, for example, you start you consider a exclusion process with next to neighbors jumps. Okay, I mean, you can jump to your neighbor, also to distant 2, let's say. Then all this combinatorics is destroyed. So, for example, and then there is this question about whether, in that case, the non-equilibrium stationary states have the same macroscopic properties of the one that you can compute explicitly.
Mm-hmm. That's interesting.
So
there is a, yeah, please.
So it's a question. Yeah, so is extension to Malia-Weinstein also possible? So in principle, so it's the answer should be yes, because so going back to the last theorem, so just giving one word about the theorem in Stein method, you have to define a Stein operator, okay. Usually, which is some elliptical or parabolic operator for which your target distribution is a stationary solution or the solution. Okay, and in this particular case, to derive this theorem here, the Stein equation that I use is just a heat equation. Okay, so it's the simplest possible equation. We know that the heat equation at any time t has Gaussian behavior, and that's basically that's it. So in principle, it's so simple as an argument that you can really extend it to basically whatever you want to extend it. It's so I would think that you can also do Malia-Weinstein with these ideas that but I have to say this this theorem I just stated is really, really, really thought to work with Markov chains, because higher order variations, for example, for diffusions, are identically zero. Because so you just have to take the scaling of these things. So if your generator is an approximation of the Laplacian, for example, you will see that the second variation goes to the square of the gradient, and the third variation goes to zero, and all the other variations go to zero too. So therefore, it's not that meaningful, this type of results in that context of diffusion, but you can also do Levy processes maybe. And for Levy processes, these variations make sense, and then you can start to think about this this type of thing.
Yeah, thank you very much. Is there another question? Otherwise, I propose that we take 5 minutes for a short break, and we thanks Milton once again, and we continue with Octavio in 5 minutes. Thank you.
Maybe we can give my slides a try.
Octavio, maybe we can try to see whether your slides work.
Let me try to share my screen.
Okay, it seems to work. They look very good, very nice, I have to say.
Can you see when I'm?
Yeah. Perfect. Did you change your affiliation, Octavio?
I did, yeah. I have come back to Brazil at the end of 2021, and have started working in Salvador last year.
Because okay, then I should change it.
I think my last paper on archive is still with the Purdue affiliation, so that's fine.
Yeah, but I couldn't find you in this. I found you in Purdue. Okay, I will take note of that. Anyway.
Should we start?
Yep.
So, welcome back. We're very happy to hear our second speaker today, who is Octavio Menezes. He was, according to my notes, in Purdue. He was a Glom visiting assistant professors, but now he is a professor at Salvador in Brazil. So thank you for being here, Octavio. And the topic is entropy estimates in interacting particle systems.
Well, thank you for the invitation. Thanks everyone that is here. So in the first talk, Milton talked about non-equilibrium stationary states and how those stationary states of Markov chain could be an interesting object of study. So in this talk, I will show you an actual models are explicit and very specific and state some very precise theorems and at least show you some ingredients of the proofs. The actual proofs are not very slide friendly, so we'll see what I can do. So that's the plan for the talk. We'll introduce the model that we have worked with, state precisely the entropy estimates, derive two consequences of those estimates that we could obtain for our model, and then try to say as much as I can about how you actually prove those entropy bounds. So let's start with the model. So our original motivation for this project was not, we did not start with non-equilibrium stationary state. We started with a nice inequality for entropies, and we started looking around, okay, what is it, what can it be used for? And we chanced upon the model I'm going to show as an example of a model where the stationary state is not explicit, but you can kind of guess that it should be close to a product measure, and then our work is to make this guess precise. So we are working on the circle with endpoints, at most one particle per site, and we superpose two dynamics. One is a simple exclusion dynamics in which the particles try to perform random walks independently, but they collide. They cannot both occupy the same site at the same time. So that's a diffusive dynamics. And on top of that, we put some birth and death dynamics, some spin flips. We fix some density between 0 and 1 rho. If a site is occupied, we kill the particle at rate 1 minus rho. And if the site is empty, we create a new particle there at a rate that is rho plus something that depends on the neighbors. If you don't have this lambda term, this dependent term, then what do you actually have are independent spin flips. If you have independent spin flips on top of diffusion, then of course your stationary state is product with density rho. Here, if we think that lambda is positive and if we add this term, then it's like the system wants to be at density rho, but it gets some extra help. So the actual density should be a bit higher than rho. And by the way, things are defined, things should be translation invariant. So the measure we set up to study is actually translation invariant. We can do some computations to show it's not a product measure if the lambda term is not 0. But we can have a pretty good guess that it should be close to a product measure. And our work is to make this guess quantitative and get as much as we can out of it to see how far we can take the entropy inequality. So that's our goal. We're going to prove things about the stationary state, about which we don't know much. It's not explicit, but we can guess it's close to some product measure that is homogeneous in space. So here's what we are going to use. We're calling rho star this density that we guess is the correct density for the system. And we are approximating the stationary measure by an IID measure with this density. And the way we compute this is by asking that under this IID measure, the expected change in the occupation of the site is 0. And this turns out not to depend on the size of the system. So it gives an equation for the density of rho star that we can actually solve. And for our specific choice of rates, there is only one solution to this equation. It's a different and very interesting problem when you have 2 or more possible densities that the system can converge to. Then it's not too clear what happens. So there have been several works in this direction by other people. So here are the measures that we are interested in. Our goal is to say something about the stationary measure. And to arrive at the stationary measure, we were going to start, say, at IID, let the Markov chain run its course, and see what happens with the law at time t. See what if we can say anything about its limit. We're going to write things in terms of the Nikodym densities between the measures we want to look at and this reference IID measure. And the way we're going to measure closeness is via relative entropy, about which Milton talked a bit in his talk. So we're going to denote by h of t the entropy at time t. This, of course, depends on what the law at time 0 is. So let's say you just start at IID with some density IID with your final density, and then the density will stay the same all throughout the evolution of the chain, but there are some correlations that they're going to be forked. And of course, we are interested in the entropy between the stationary state and the IID reference metric. Our goal is to estimate those things and then see what we can deduce from such an entropy bound. So our actual statement here is the model again. You get exclusion dynamics at a rate n squared, at which you expect to see a limit. And we get this reaction diffusion dynamics. So we get this perturbation of the IID of the independent spin flip, and we can expect the system to be close to product if the perturbation is small. So if the perturbation is small enough, then we can have dimension-dependent estimates for the entropy. In all cases, the entropy is much smaller than the volume of the system or the number of sites. And by way of comparison, the method we're going to use based on Gauss inequality has been used many times to prove laws of large numbers for the density of particles in particle system. And usually for those laws of large numbers, the theorems, you need bounds that are much smaller than the volume. You can get much smaller than the volume and quantitatively so. Once we have the dynamics, the stationary measure, we guess for an explicit measure that should approximate the stationary. If we have those bounds about which we will talk in the second part, what can we say about the stationary measure? One of the computations we can do is, we have to call it conservation of local equilibrium, but I guess there are several statements that deserve this name. So let's stick to d equals 1. And one thing we could do is to look at the occupation of a site, eta x. It tells you if there is a particle there or not. We center it, not by the actual expectation, but by the guessed density. This is the density they would have in the law of large numbers, and we try to see if this concentrates, if this is close to the measure. So test it against a function, against a smooth function, and compute the variance. The variance under the stationary measure it goes to 0 with the size of the system, with the explicit Plater conversion.
Sorry, it is square of the sum, not the sum of squares.
It's the square of the sum. This is the variance of the. It's the variance of the integral of f against the empirical measure.
Thank you.
So this is the type of result we would like to prove. We can do a little bit better if instead of looking at the occupation of a single site, we look at some local function, look at some function that depends on what happens on a neighborhood of this, say a neighborhood of 0, say a function that looks on, say some polynomial on the occupations of the 10 sites to the left and to the right of 0, say. So we can take a function of this type, and again, subtract not its actual expectation, but its expectation under the IID measure that is supposed to approximate the stationary state, test it against the test function, compute its variance, and again, we get something that behaves very well with the size of the system. And we also get some more explicit error terms here. In particular, the size of the support, of course, should matter. And there's a constant implied here that involves the infinity norm, or rather the amplitude or oscillation of the function. In any case, the general case is almost as easy to prove as the special one. And this is the type of thing you can get more or less easily if you have two ingredients at your disposal. One is a good estimate on the entropy, as we do, and second, if your reference measure, in our case IID, has good concentration properties. And for us, we do have an IID product measure. So here's the variance we try to estimate. And of course, we also have similar results in dimensions 2 and 3, and they're all proven together. I just chose to focus on d equals 1 to simplify things for the talk. In any case, it's always the same thing. Look at a local function, subtract its guessed expectation, so to speak, average out in space. So we are taking advantage of the translation invariance of the dynamics and of the measures here, and see what bound you can get. And turns out you can get bounds that are good. They in particular, they imply easily a law of large numbers for the density. It shows you that if you look at a macroscopic box, then the number of particles inside that box is actually close to rho star times the volume of the box. And the way you do one of those proofs, we are going to use that inequality that Milton wrote in his talk about they use the variational characterization of entropy. And essentially you can replace an integral under the stationary measure by an integral under the IID measure, as long as you pay the price, double price of one entropy, and two, you replace the thing you want to compute by its exponential moment. So on the one hand, you need some work to estimate the entropy, and on the other hand, your reference measure better be so good that you can do exponential moments of whatever you want to estimate, which in our case here is basically a sum of IID things. So exponential moments of sums of IIDs, that's done. And if instead of looking at the occupation of a single site, you look at a local function, then there's some extra steps, and you get that extra factor with the size of the support. But it's basically two steps. Use your entropy to change the measure, and then use the explicitness of your reference measure to estimate your exponential moments. And so far, some people have already used those types of entropy inequalities for proving different things. And in all of the works that I'm aware but one, the reference measure is always product. So you can exactly so that you can compute those exponential moments that you were stuck with if you want to do your estimates. Essentially combine those two, and then you get your bound as we have written here. The variance is of order 1/n in dimension 1, and you get the size of the support. And the size of the support is important to have for the second corollary of the entropy bound, because how far can you push it? You can push it, say, to square root of n or even bigger. So what you can do is a sort of approximation of the stationary measure by the IID measure in total variation on a mesoscopic box. The size of the box is dimension dependent. Here we do dimension 1, so we can have an explicit formula. But essentially, you can throw in any bounded function of the configurations, and its expectation will be very similar either under stationary or under IID. And again, this is very specific to our model because we have translation invariance, so we can rewrite an expectation of this type as a spatial average. You can write one of those integrals by the spatial average of the expectation of its translates, just because both the stationary measure and the IID are translation invariant, so we get this. So you get this rewriting, and then you can do say G-Schwarz to take your expectation inside, and you were. See, there's a typo here. I should have integrated against the stationary measure in this slide, not the IID measure. It is that you regard the integral against rho as a constant as you integrate with respect to the stationary measure. Then, well, once you do it, you are back in the previous result. get an estimate of the variance of the spatial average of a local function. And you just plug in the bounds we had involving the size of the support, and there we have done the computation also for other dimensions, and depending on the dimension you can push this approximation to different sizes of boxes. But then those are things you get to do if your reference measure is good to work with, such as IED, and if you have a good estimate on the distance. Then, of course, the hard work goes into the proof of that entropy inequality stated at the beginning. So several people have used either the inequality or its proof method to do different things. We have stumbled upon it while doing random walks on dynamic random environments driven by the exclusion process, and since then we were able to apply it to some other contexts. And as I mentioned, all of the works I have looked at, they compare their Markov chains with product measures, with the exception of this last work by Borinu and Tegalier, which is a really nice work. They managed to come up with a whole family of correlated measures, which you can tune not only the means but also the variances. But as you will see shortly, even for product measures, the computations already can get quite involved. So let's now have a look at what goes into the proof of the entropy inequality, starting as general as I can manage. So we start with the Markov chain in finite space with some generators, some jump rates. We are going to use this Cavedo-Champ operator to just take the formula for the generator applied to a function and square the differences. And the reason we work with these operators is that it will play the role that is usually played by the Dirichlet form in such inequalities. Because we're not dealing necessarily with invariant measures, we don't really have Dirichlet forms, but we can integrate the Cavedo-Champ. So let's say you are on this general finite state continuous time Markov chain setup. What you can do is the following, and this inequality is well known since the 90s at least. So what we have on the left-hand side is the entropy between the law of the Markov chain at time s, that of course depends on the law of time 0, against some measure, some reference measure, which up to now is completely arbitrary. And we can bound how fast this thing grows. So it turns out we can upper bound the time derivative by a sum of a negative term, which is given in terms of this quadratic operator, and a term that can make the entropy increase, but a term that is very explicit. You can compute this adjoint generator explicit in terms of the jump rates, and if your reference measures are explicit enough, you can also compute how this term here changes. So this inequality is probably much more familiar in the case where your reference measure does not change with time and also coincides with the invariant measure. Then what this inequality says is that the entropy between the chain and the stationary state decreases in time. And it even decreases even exponentially. So you don't have this second entropy production term if your reference measure is the stationary measure. So things get much easier when you're doing a stationary measure, and then the integral of the Pareto is it coincides with what is usually called the Dirichlet form that people use when they state inequalities such as spectral gap inequality or the log-Sobolev inequality or other inequalities of this type. So these are our building block, and our job is to choose good measures. They have to be explicit enough that we can compute things and do the estimates we need, but they have to be close enough to the actual law of the process that the resulting estimate is useful. So essentially, we are going to hammer at Gauss inequality until we can bound enough terms. And what is involved is, well, the inequality I have just shown. In the first couple of corollaries, the variance estimate and the total variation estimate, we have seen how it is convenient that your reference measure concentrates well. That's why most people have worked with product measures so far. And then there's a certain estimate that we have to do, and which is purely analytical in a sense. And that you forget about the dynamics and you're just trying to estimate some integrals. So you have to estimate integrals of arbitrary against arbitrary densities of certain functionals. The functionals are those that show up in the entropy production terms. And you have to somehow estimate these in terms of the Carré-Duchamp operator and the entropy itself. So those are the basic ingredients. With those, you can get an entropy inequality that behaves well with respect to the size of the system, but you have estimates which are bad for large time. So if you want to say something useful for large times, then those need to be combined with inequalities such as the log-Sobolev inequality, in which you bound the entropy by the Dirichlet form, or in our case, the Carré-Duchamp. Some cases, like in our model, you can just make use of a log-Sobolev inequality that is already done, and in other models you have to adapt. So how do you bound those things? So your goal is to eventually bound the time derivative of the entropy, and it all hinges upon this adjoint term here, which is explicitly computable. And even in the simplest cases, it takes some work to compute, but the formulas that come out are not entirely meaningless. So just as an illustration, here is what comes up if you compute this term in the simplest model you can think of, which is just a symmetric exclusion, but you approximate with a family of product measures whose parameters are changing with time. So you can, your reference measures are IID. You can write things in terms of mean zero IID variables, and the thing you need to estimate turns out to be expressed as a polynomial in those IID variables. So if you choose your averages in a way that you don't get a linear term, then you are left with a quadratic term for which we were able to bound in terms of the Carré-Duchamp. So this is the type of thing that shows up. And here's some other examples of works that have used the inequality in one way or another. Then in almost all cases, you are dealing with product measures. You have this recent work, which was the first one to allow for more than one particle per site, which was something I was very interested in doing. Then you always have those very explicit things. So if you want to estimate things, you need to be explicit. So in our model, since everything is translation invariant, and since the reference measure is IID, then the actual thing you need to compute is not so bad. It's still a quadratic type term. It gets smaller when your perturbation gets smaller. It gets smaller when your perturbation gets smaller, and then the type of thing we can prove is here's where the lambda in the term comes from. That's the strength of the perturbation. So here's the inequality we are able to prove. I can try to say something about the computation. So you bound integral of the adjoint against an arbitrary density in terms of Carré-Duchamp operator and the entropy itself. You combine this with a log-Sobolev inequality, which bounds the entropy by a multiple of the Carré-Duchamp operator. Now, for us here, for this model, we could do we could just use the log-Sobolev inequality that was already proven, because it's basically spin flips, with finite range spin flips against an IID measure. So this result is already known. I forgot to write down what the Carré-Duchamp associated to the exclusion is, and my writing equipment just failed on me. But so what goes on in here is the sum of the squares of all the gradients of the square root f, in which you switch to neighboring. You switch the occupations of two neighboring sites. And well, if you can combine this sort of analytic estimate with a log-Sobolev inequality, then you can say something about the entropy that is good for all times and push it to the entropy at the stationary state. Let's say you can start at any configuration, so might as well start at IID, zero entropy, as the dynamics goes on, you expect entropy to increase a little bit because correlations will form. But if things are to stay close to product, then entropy better stay bounded in time. So we do this, we apply a Yellow's inequality, and estimating this term, we want to arrive at some bound for time derivative that has a negative coefficient in front of the entropy. Then you can do one or some elementary argument to argue that your entropy stays bounded in time. You can integrate this in time and say that the entropy remains bounded. So in the first step, you plug in our first inequality, the estimate of an arbitrary density. And on the second step, you replace this entropy here by another Pareto term using log Sobolev. So the log Sobolev uses is what deals with this blue term, and you add and you take away, again using log Sobolev, you add and take away the term that he wants to show up in the term that he wants to show up in the final inequality. You want time derivative of the entropy to be bounded by a negative multiple of the entropy itself. So here we have the upper bound we need. We just need to somehow get negative things less term. And here is where we need our strength of the perturbation to be small. So there's a constant that shows up in the first bound, the bound of the arbitrary density, in which you have a constant in front of the entropy that depends on the coefficients of your quadratic function. We're going to have a look at where this comes from. And essentially it depends on the size of your perturbation. So if your perturbation is small enough, you can get your positive terms small enough to get something small at the end and bound by the entropy uniform in time. Can do something similar in dimensions 2 and 3, but the computation is more involved. As I mentioned at the beginning, those proofs are not very slide friendly, but I guess we can at least highlight the main ideas. So what is left for us to do is to actually say something about how you bound expectations of quadratic averages, spatial of quadratic averages under the IID measurement. And well, this is the more technically involved part. Our model is, I think it's as simple as it gets. The reference is IID. Everything is translation invariant. The coefficients are easy. Even so, we do have to work a little bit. So we'll try to say something about the type of things that you have to do. Essentially, we can break an estimate of this type into two steps. First, we're looking at a sum of local terms. we're looking at a sum of terms that depend on only a couple sites, and we're averaging this over space. So the idea is to replace each of these by spread those sums, replace each of those terms by a spatial average, then bound the spatial average in terms of entropy plus the concentration inequality, as we have done in the corollaries at the beginning. And it turns out that the difference between the local term and the averaged out term, you can decompose it into sums over different sums over neighboring sites, over adjacent transpositions. And there are some tricks involved. So here is the idea. You start with your local function. In our case, it's just eta x. It's not more complicated. You define some averaged out version of it. You can average in a box to the right, and you can do something similar in higher dimensions. Here's the function you want to estimate. It's a sum of local terms with weights given by some function g. And here's the averaged out term that you hope to be able to control with concentration. When you compare those, you are comparing a function evaluated at a point with its average on a region. Turns out that you can decompose this blue part here. Turns out that you can decompose decompose one of the measures, namely the point mass. You can take your point mass and carry it into a different measure, an average, by throwing mass around. And if you do it in the right way, then you can write everything in terms of nearest neighbors. Once you do this, then you have something that you can bound by the Carré-Duchamp term. So in one dimension, it's an algebraic identity. In 2 and 3 dimensions, there is a geometric argument that is involved here. So this part here is just a rewriting, just to say that the difference you can bound in terms of the Carré-Duchamp. There's something extra that remains, and this you have to estimate by concentration inequalities. And you also have to estimate by a concentration your averaged out thing. So this is the basic structure: replacement and concentration. And each of these steps needs to be worked at. And it turns out that if you do this uniform average as I just did, the concentration bound you get under IID is not good enough. So you need to average with respect to a smoother kernel, and there are things involved in here. So this two-step inequality, which is averaging and then concentration, it works on our model if you choose the right kernel, the right way of averaging. It doesn't work in general situations where your product measure is spaced inhomogeneous. Then you have to do some more work and do some extra inequalities. In any case, just to finish, we'll try to summarize. The hard work is hidden inside. The hard work is hidden inside this inequality here. For a certain type of a certain class of functions, you have to bound arbitrary densities by the coefficient and the entropy. This is a purely analytical lemma, if you will. This determines if your bound will be good enough or not. And that's where the hardest work is hidden. As long as you have that, then the rest is more or less standard. So you start with something to control the entropy increase. You need your reference measure to concentrate well. So you want to. So every time you use the entropy inequality, you want to be able to compute what is to compute the exponential term that will come out. And if you want estimates that work well in time, then you need something like log subgraph. So that's the basic structure. This is what we did for our reaction diffusion model. So we were able to show for this specific model that the stationary state is very close to the product measure that you could guess, and then we could prove very precise bounds in this approximation. So I guess that's what I have to say. Thank you very much.
Thank you very much, Octavio. Are there questions? So maybe I would like to hear again the interpretation of your result. So you start by saying there is a product measure that should be close to stationarity, and then you are allowed to get very precise bounds of how good was your guess. That's a good way to.
Yes. By the way that the model is set up, you have diffusion and you have basically independent spin flips, but you perturb the flips a little bit to add correlations. So by the way the things are set up, you can guess, okay, I think this will be spatially homogeneous and it might even be close to product. So okay, if it is to be close to product, that would be the density. So let's see if we can prove it. Let's see if we can say something quantitative about this approximation.
Great, that's very nice. Now, Alessandra has a question.
Yes, thanks. So thanks for the talk. I have two questions. So at the beginning, you have discussed an application to get some bounds. Do you expect these bounds to be optimal or almost optimal?
I expect these bounds to be optimal. I don't have a really good argument in support of that, but yeah, that's my guess.
Okay. So thanks. And the second question. So in the dynamics, the reaction term is given by lambda, and then okay. So it's proportional to the number. So one rate is you have a correction, a perturbation, proportional to the number of particles in the nearest neighbor sites. But can you extend your results, your method to more general expressions? Or you really need this particular form in order to apply all the machinery?
I think finite range should be enough. I think finite range should be fine.
So you mean a function depending on the particle configuration around the site X, which is finite range? You mean this?
Yes, yes. What
Okay.
could go wrong here? What could go wrong here, depending on how you choose your perturbation, is what could go wrong is that you could have more than one attracting density. There are some models that have been studied by Landin and Sonoda from the large deviation principle point of view, in which they also have reaction diffusion, but there's more than one density that the system can converge to, and then it's not clear how the method here would work. We don't know what would happen.
Okay, thanks.
Yeah, please, Andre.
Thank you. Interesting presentation. Questions also that I have. Firstly, bulk of what you did relies on symmetric simple exclusion process, SSEP. Could this be used also for ASEP, TASEP, and maybe even SIP? Could this be extended to other interactive particle systems? And secondly, related to first lecture of Milton, could you use Stein inequalities to derive something like this? Log-Sobolev are quite usual, I think, in these cases for SSCP and similar, but could also Stein, I don't know, be of any help? Thanks.
Okay, about the first question, the entropy method has been used for weakly asymmetric exclusion process with it was successful there. I don't think it would work for asymmetric process. I don't think you could get a good product approximation at least. So at least with the machinery we have now, I don't think it would be doable for asymmetric. Can you repeat the second question, please?
So I was also asking about SIP for inclusion processes. Could this be used, but it's also symmetric.
So SIP for inclusion, I think it should work because you have explicit product measures that have very nice identities of the generator. So okay, for SIP it should work, but not in all cases, because for SIP you can have condensation depending on how you choose the parameters. So in those cases, a product measure would simply not be a good approximation. But, well, under some assumptions to guarantee that SIP is diffusive enough, I think the method should work.
Thanks. And also about Stein, would any other concentration inequality or inequality approach be used for driving the proofs and bound?
Yeah, this one, I don't know.
So if you allow me to, maybe I can comment a little bit on that. No. So from just comparing with what happens with continuous time systems, no, or diffusions, things like that, where things are much well understood. This type of machinery, functional inequalities, entropy bounds, variational principles, they work very well, but always you need some sort of ellipticity condition. For example, SIP doesn't satisfy that ellipticity condition because the diffusion coefficient when the density goes to zero. That doesn't actually, that's what it causes condensation. So that's that. that's really annoying for this methodology. I mean, in some situations you can overcome that, but that requires a very clever argument. But aside from that, all this machinery works very well if you have some sort of ellipticity going around in your system. About Stein methods, and so there is a discrete systems. They have this problem about somehow large deviations. So it's very easy to create a large deviations because of the jump. So in a sense of when you look at just the Markov chains, or let's say Poisson processes, a large deviation function of a Poisson process, it decays very slow at infinity. It's convex, but it's only x log x. That means that you can create a very large deviation with a little bit with not much effort. So that means that you can't really use anything better than relative entropy unless you know something more about your systems. So that's why in this methodology that tries to be as general as possible, relative entropy is kind of the best that you can hope for. Well, I think that's what I can comment about.
Thanks. Yeah, thanks. More than clear. Back for the first question.
Okay, so in case there are no more questions, we thank Ottavio and Milton once again for these very interesting talks. And in 2 weeks, help me with this one, Alberto. What happened?
In 2 weeks, we will have Fabio Toninelli and from University of Vienna and Giuseppe Canizzaro from University of Warwick, speaking about a topic to be announced very soon. And so see you all next week, in 2 weeks, and I wish to thank you again, Ottavio and Milton, for giving